video will be on solution of heat equation in one dimension, and you can see the equation c square times del square u over del x square is equal to del u over del t. It is a non-homogeneous heat equation, right? And why we are calling it as non-homogeneous? Because this is a second order partial derivative and this is a first order derivative, right? And however, it's a linear equation, as all the derivatives are appearing with a degree of 1, right? And as compared to the wave equation, as we did in our last video, you can see that there is a slight difference in the equation of this heat equation. Here in wave equation we had UTT, right? The derivative with respect to t is now the first order derivative in this heat equation, but due to this slight change, the solution is changed drastically, right? And we will see that the solution of heat equation differs from that of the wave equation in a quite different way. And first I will give us a small brief of its modeling, right? How the heat equation is modeled. So you have to consider a thin homogeneous rod or homogeneous rod of length capital L, perfectly insulated curved surface, right? I should write it in bracket. So you need a homogeneous rod of length L, and that should be perfectly insulated curved surface. Means you can think this marker as a thin rod, right? And its curved surface, this surface, right, is perfectly insulated so that no heat can escape from its curved surface, right? Placed along x axis with the ends at x equal to 0 and x equal to capital L, right? And yes, so the left end is placed at the origin and the right end is placed at the coordinate L comma 0, right? And yes, the temperature distribution denoted by u as a function of x comma t. X is the x coordinate along x axis and t is the time and u is the temperature, right, is given by the solution of PdE, and that is del u over del t 1 over c square is equal to del square u over del x square, and this is called heat equation, right? Heat equation or diffusion equation, and where c square is T sigma rho, right? Where T is called thermal conductivity, and this sigma stands for specific conductivity, and rho is for density of the material of rod, right? And that ratio is taken as c square because that is positive, right? So you can see that this heat equation is very similar to the wave equation with a slight difference of this derivative with respect to t, right? We have first order derivative here in the heat equation, while in wave equation we had this second order derivative, right? And you can see that you need a thin rod with for your experiment and with some temperature on it. This is a key point because we are going to discuss the heat flow, use the temperature or temperature flow or temperature distribution at any point and at any point on in rod, right? And for that you need some temperature, initial temperature on the rod, right? And there are so many cases, if you place the rod over x-axis and at its ends are kept at 0 degrees Celsius, right? And the other case is that when the ends are perfectly insulated. I will be going to discuss them one by one. So first case I'm going to discuss is the rod with ends at 0 temperature, right? Okay, so let me write here. There are, I should write case number 1 directly. Case 1, case 1, case 1, ends are kept at 0 degrees Celsius or 0 Kelvin, whatever, okay, or 0 temperature, 0 temperature, right? In that case, the heat equation becomes 1 over c square del u over del t equal to del square u over del x square, right? And first condition, the left end of the rod is at a 0 degrees Celsius, right? Probably you are putting an ice cube here at this end and this end, right? Okay, so u 0 comma t equal to 0, which indicates that for any time t the left end is at 0 temperature. And the second condition is the right end x equal to L for any time t is at 0 temperature, and the t where for t greater than 0, right? And third condition is u x comma 0 equal to fx. It indicates that at the initial time when t is equal to 0, the rod has some temperature on it. As I said earlier, that you need some temperature, right, in order to allow the flow of heat throughout the length of the rod, right? So you have some initial temperature that is depending on x, right? Here t is equal to 0, initial temperature, and that may be of any form, means triangular form or sine form, cos form, anyone, right? And for all values of x, lying between 0 to L, right? So these are the initial and boundary conditions on the rod. Now, solving this heat equation as we did earlier by using the method of separation of variables, I will be taking u is equal to capital X times capital T and then substituting that in my equation. I will be getting two ordinary differential equations, then allowing these conditions on that solution, I will be getting some solution, right? And of course I have to use that Fourier series, Fourier sine or cosine series, as I used in my wave equation video. Okay, fine. So starting with the solution of this heat equation, let u as a function of x comma t is equal to capital Xx and t be the solution of this wave equation, right? And now substituting these del u over del t and del square u over del x square here, substitute in this 1 over c square ut is equal to u double x, we get, I think, 1 over c square, and del u over del t will give x t dash equal to x double dash t, right? And then bringing the x and t terms on both sides of this equation, I will get, or 1 over c square t dash over t equal to x double dash over x. And we can see that the left hand side is a function of t and right hand side is a function of x, and if the two functions are equal, different variable functions are equal, they have to be equal to be some constant, and that constant is called separation constant, k, say, right? This is called separation constant, right? And then you will get two different ordinary differential equations from here. The first will be, this gives, the first equation will be x double dash minus kx equal to 0, first equation, and the second equation will be t dash minus c square kt equal to 0. This is my second equation, right? And you can easily solve these ordinary differential equations, and this x double dash is del square x upon del, sorry, d square x upon d square, the ordinary second order derivative, and t dash is actually equal to dt over dt, first order derivative, right? Now I'm not going to solve these equations, okay? So rather I should allow these conditions here, right? Okay, fine. First I will use this condition, boundary condition, these two conditions. Here is my solution, this is my solution. Let it be equation number A, right? Okay. The point should be sign of k, right? Nature of k, the separation constant. That what should be the sign of the separation constant, as we discussed in wave equation, right? So first, using first condition, u 0 comma t is equal to 0 gives, using this in A, right? In A, that will give me x0 tt equal to 0, and that will produce x0 equal to 0. And notice that you cannot take tt equal to 0 because that will give me a 0 solution, right? And this is very much similar to the solution of wave equation with the bounded interval, right? Okay. So this is x0 equal to 0, and using another condition, condition number 2, using second condition, I will get u l comma t equal to 0 in A, and that will give me x l equal to 0, right? Fine. So now I will be going to discuss the sign of k, right? First I will take first case. I should write it A. If k equal to 0, if k is equal to 0, then equation number 1 gives x double dash equal to 0, and then on integrating it twice I will be getting a linear function, and that is equal to x as a function of x is equal to ax plus b as solution for this equation number 1, right? Okay. And then imposing these two conditions, this one, if I impose this condition x0 is equal to 0 here, then I will be getting b is equal to 0, right? And on imposing the second condition, I will get a is equal to 0. So as a whole, on imposing, using x0 equal to xl equal to 0 gives a equal to b equal to 0, that is xx equal to 0, right? And on after getting xx is equal to 0, and on putting this value here, I will get u is equal to 0, a 0 solution that is of no interest, right? That is, or uxt comma equal to 0 solution, and that is always avoided, trivial solution, right? So we cannot take a k is equal to 0. Now if k is negative or positive, sorry, k is positive, and let me take it first, gives this first equation, this is my first equation, x double dash, and k is negative, that will give me k is positive, sorry, minus p square x equal to 0, where I have taken k is equal to some positive value, right? It is always greater than 0, right? Because p is a real number and the square of any real number is always positive, right? So you need k positive, substitute k is equal to p square. Then it will give me, then x as a function of x will be equal to plus minus p will be the answer, capital A e to the power px plus capital B e to the power minus px is solution, right? And on this solution, imposing again these two conditions will give me capital A equal to 0 and capital B equal to 0. You can verify them easily, right? Using x0 equal to xl equal to 0 gives capital A equal to capital B equal to 0, and that will produce x equal to 0, and ultimately uxt equal to 0. Again a trivial solution, right? So again we have to avoid this positive value of k, right? And taking last possibility for the sign of k. Okay. Third, C. If k is less than 0, right, then first gives an ODE of the type x double dash plus p square x equal to 0, where k is equal to minus p square negative, right? Fine. Then solution will be x as a function of x is equal to capital A, or I should write it as C1 C2. C1 cos px plus C2 sin px, where C1 and C2 are arbitrary constants, right? And now imposing that this condition, x0 is equal to 0 and xl equal to 0, using x0 equal to 0 on this solution, I will be getting C1 equal to 0, right? Gives C1 equal to 0, right? That is x is equal to C2 sin px is the refined solution with the lesser number of constants. Only one constant is there, right? And now on imposing second condition, xl equal to 0, using xl equal to 0 gives, if I put x equal to capital L here and then equate to 0, then I will be getting C2 sin PL equal to 0, and of course you cannot take C2 is equal to 0. If you take C2 is equal to 0, then on plugging that C2 equal to 0 here, that will give me a 0 solution, and I will avoid every constant that will give me a 0 solution, right? So that will give sin Px is equal to sin PL equal to 0, right? And that implies P equal to n pi over L, and n is any integer, right? You know that sign is 0 for every integral multiple of pi. So this is a P, and you can substitute this P here as well as in this equation, the equation in time t is a t, yeah, this equation, right? Okay. Therefore, x will be ultimately equal to C2 times sin n pi x over L, right? Is a solution. Is a solution of this first ODE, not full solution, right? Is this one, right? And what is this n? As you can see that n is any integer, negative as well as positive 0 also. But here I have to write n is equal to 1, 2 and 3, and you should know the reason why I have avoided the n equal to 0 and the negative values of n, right? The reason is that I have avoided n is equal to 0. Why? Because on putting n equal to 0 here, right, that will give me x is equal to 0, again a 0 solution, right? And that's why I have avoided n is equal to 0. And why I have avoided the negative values of n, minus 1, minus 2, minus 3, so on, because on putting n equal to negative, suppose you put n equal to minus 1, and that minus 1 will appear here, and that gets absorbed with this constant. So writing an arbitrary constant before some function, right? So there is no need to overwrite or overcount the solutions, right? N equal to minus 1, minus 2, minus 3 are already incorporated in this solution due to the presence of this constant, right? Okay. So no need to overwrite the solution, just start from n equal to 1, 2, 3. Okay. So this is my x in terms of small x. Now what do I need? I need tt, capital T in terms of small t, and for that I have to plug in this p. Where is that p? Yeah, k is equal to minus p square here, and then I will solve this equation. And that is of course in first order ordinary differential equation, which is quite easy to handle. And let me write the solution of this T equation, equation number 2. Now taking equation number 2, and the solution will be T as a function of small t. Let you focus on this equation and remember that k is equal to how much? Minus p square, and that is accepted. So I will put a box on it, and if you put k is equal to minus p square, that will be c square p square t, and that will give me tt is equal to some constant, let it be c3 times e to the power minus, I think, p square, yeah, c square p square and small t, right? Fine. And you can plug in this p from here, that will give me equal to c3 e to the power minus c square n square pi square over L square t, right, is the solution for this second ODE in capital T. And after getting x and t, I can plug these values in my solution. Where is my solution? This is my solution, equation number A. Then therefore ux comma t equal to xx multiplied by tt, and you can see that when you multiply these two, c2 and c3 will be available as a product, and that can be written as a new constant. Let me write that constant cn, and of course that cn is equal to c2 c3, right, and sine n pi x over L multiplied by exponential function c square n square pi square L square t, right, and this will be the solution. And again you notice that this n, small n, runs from 1 to 3, so you can put a summation here, and starting from n equal to 1 to infinity. This is the solution, defined solution. I will not put a box on it. Okay, is the solution, right? And now you can apply this third condition. If you remember the third condition, that is ux0 is equal to fx, that is the condition for the initial temperature distribution over the rod. Using third condition is solution, right? Third condition, that was ux comma 0 equal to fx. This was my third condition, and you can use this condition here. I will get fx equal to summation n equal to 1 to infinity, and the cn sine n pi x over L, and this is going to be e to the power 0 will become 1. And to find this cn, you should remember that half range Fourier sine series, because this fx as a function has been expressed as a sum of sine functions, and this is what we call it Fourier sine series, right? And the Fourier, this is called Fourier sine coefficient, and this, that is given by cn equal to 2 over capital L, and integration runs from 0 to L, and this fx sine n pi x over L dx, right? So this is the final solution. Is after getting this cn, you will plug this cn here, right, and that is called the final solution. I can plug this cn here. Then ux comma t equal to summation n equal to 1 to infinity, and the value of cn is 2 by L, 0 to L, fx sine n pi x over L dx, and that multiplied by e to the power minus c square n square pi square over L square t is a solution, right? So this is the solution for the case when the ends of the rod are kept at 0 temperature, right? Okay, let me take few examples for this case. And what you have to remember, either you remember this solution if you want to apply it directly, or will take this solution, where is that? This solution, this one, right? In this solution, condition number 1 and 2 have been incorporated, right? The 0 and conditions are incorporated here, and according to the numerical, the fx will be given, and we will use this condition number 3. So in numericals, I will be taking this solution, this one, right? I will put a star here, right? In this solution, we have already incorporated 2 of our initial conditions, boundary conditions, that is u0 t is equal to 0 and ul comma t is equal to 0, that the condition for 0 end, right? 0 temperature at both the ends. Okay, I will be taking this fx as a function of x in examples, right? So let me take an example on the same case when the ends are kept at 0 degree temperature, and the initial temperature distribution is given by some function, right? And example number 1, solve u t is equal to c square times u xx for subject to the first condition is same, u0 comma t equal to u l comma t equal to 0, right? And t is greater than 0, right? And L is the length of rod, right? And the second condition is this condition, u x comma 0 is given by some function, and let me take that function as x for 0 to L by 2, and here L minus x, L by 2 to L, fine. This is a triangular function, right? And yeah, L is the length of rod, where capital L is the length of rod, right? So I will start the solution from here. Where is that? This solution with this first condition already incorporated, right? And solution, the solution using this first condition, first and second are both in this condition, using first is given by u x comma t equal to summation n equal to 1 to infinity, and this Cn sine n pi x over capital L. Make sure that your length of the rod is again capital L, right? Fine. And e to the power minus c square n square pi square over capital L square times t, fine. Okay, so this is a solution, right? Now the remaining condition is this condition number second, right? And to impose this condition, I will, using condition number second, this one, I will be getting fx is equal to summation n equal to 1 to infinity Cn sine n pi x over capital N, and this will e to the power 0 will become 1. Now comes the Fourier sine series, as we can see from here, and where Cn is given by 2 over capital L integration 0 to L this fx and sine n pi x over L dx, right? And you can use this fx from here. This is the fx, let me call it fx. Okay, you can see that fx is defined for 0 to L by 2 and L by 2 to L, right? Piecewise defined. You have to break this 2 by L, and the first is 0 to L by 2, that is x times sine n pi x over L dx plus 2 by L times L by 2 to L and L minus x times sine n pi x over L dx. Fine. Now we have to integrate this. Now performing integration, I will be getting first function, integration of second will be minus cos n pi x over L and n pi over L, right, minus 1, and it will become minus sine n pi x over L and n square pi square over L, right. And for this term, plus 2 by L minus x, this will be same, minus cos n pi x over L over n pi over L, minus the differentiation of this term will be minus 1, and again minus sine n pi x over L over n square pi square over L square, L square. Fine. The limits for this is 0 to L by 2 and L by 2 to L, right? And if you put the upper limit, there is a L by 2, here will be L by 2, and here I will be have L will be cancelled, n pi by 2, cos of n pi by 2, twice 2 by L, and here I will have L by 2, and LL will become L square over 2n pi, fine, and minus sign will appear here, cos n pi by 2, fine. And this term L by 2 sine n pi by 2, right, that will become, I think, plus L square over n square pi square sine n pi by 2, fine, and putting 0 will give 0 and 0, okay. Similarly, putting limits here, 2 by L, putting upper limit will give 0 and 0, okay, fine. Putting lower limit give L by 2, L by, okay, that will be give me L by 2 will minus L square over 2 n pi, and here I will have cos n pi by 2, and putting L by 2 here will give me, that is my lower limit, L will give 0, putting L by 2 as a lower limit, so I will be getting here opposite sign, plus, fine, okay. And this will minus, minus, plus, minus, and that will again become plus, I think, plus, right, okay. That will give me L square over n square pi square and sine of n pi by 2, okay. And I think these two terms will be cancelled, this term and this term, and we are left with this 2 by L, that will become 4 L over n square pi square multiplied by sine n pi by 2. This will be the value of the Fourier coefficient Cn, and you know that n starts from 1, 2, 3 and so on, right, n equal to 1, 2, 3, fine. So putting this value here in my solution, where is my solution? This is my solution, let me call it equation number A. Then A gives u x comma t equal to summation n equal to 1 to infinity, and the value of Cn is this thing, 4L over n square pi square sine n pi by 2 and sine n pi x over L e to the power minus c square n square pi square over L square t is solution, right? So this is the final solution. This is cap n pi by 2, right? This is 2 n pi by 2. Okay, and you can see that if you put n equal to 2, 4 for even values of n, this solution will go to 0, right? And also modify this solution, right? For writing this is because this solution will be non-zero for odd values of n, and replacing this small n by 2k minus 1, I think you can write in that way also, right? Fine. So this is the required solution. Okay, so this is the case when your rod of length L with its ends are kept at 0 temperature, right? And the second case will be we'll be discussing that case in our next video. The second case will be the rod when the rod perfectly insulated its curved surface and as well as its ends. That will be the part of our next video. For this video, thanks.